Okay, welcome everybody to VSPG. Today we're going to hear from Dr. Gerya on segmentation of subducting slabs and its implication for the onset of modern plate tectonics. Really cool topic. It's pretty relevant to a lot of the people who have been interested in joining in for the discussion on Precambrian plate tectonics, particularly the onset. So this is a great one. So I'm going to go ahead and introduce Taras for us. Dr. Taras Gerya's research uses numerical geodynamic modeling to better develop our understanding of plate tectonic processes like continent-continent collision, plume lithosphere interactions, mid-ocean ridge spreading, slab subduction, which we are going to hear about some today. Taras received his master's in geology from the Tomsk Polytechnic University and his PhD in petrology from Moscow State University in Russia. In his PhD, he studied metamorphic petrography of granulate facies metamorphism. After his PhD, Taras worked as a research associate, senior researcher, and head of the Laboratory of Metamorphism at the Institute of Experimental Mineralogy of the Russian Academy of Sciences, and as an associate professor, the Geological faculty of Moscow State University. Since he has spent some time as a research fellow and guest scientist at the Geological faculty of Ruhr University in Bochum, Germany, before he arrived as a senior research scientist and lecturer at ETH Zürich, Department of Earth Sciences, which is where he is presently professor today and continues his work. And without more, Taras, I'll let you go ahead and start your presentation. Thank you.
Thank you, Alex. So what was driving me into the profession is romantics, so of new discoveries. This is why I was educated as a field geologist, but then I found out that I like quantitation and gradually drifted toward, numerical modeling. But I'm going to try to prove that numerical modeling is also a tool for discoveries, and then you can, find new processes and phenomena on your computer screen, and then you will be able to discover them in data in nature as well. So this is a collaborative work that we started back in 2015 with Dave Berkovici when he arrived to ETH to work on implementation of new physics into the numerical models of subduction. And then Thorsten Becker joined this effort, and this is what we came with, segmentation of subducting slabs and its implication for the onset of modern plate tectonics. So without going into any more delays, so here is the picture of plate tectonics, moving plates, which in general imply that there are rigid plates and weak boundaries, and we are quite clear that plates should be strong in order to preserve their coherency at the surface. But we are not so much sure about slabs. So when these plates are starting to dive into the mantle and start their journey in the mantle, do they remain strong or do they become weaker? And there are various ways of approaching this, the answer to this question. And one way is, for example, to use experimentally calibrated rheologies and try to run models and see, what kind of viscosity contrasts and plate rigidity will be obtained in the Earth's interior. And very often these experimentally calibrated flow laws, they're showing that plates are, quite rigid in the mantle. They have, due to the low temperature and the activation of brittle deformation mechanisms, they have quite a high viscosity, and viscosity contrast with the surrounding mantle is on the order of 10 to 1,000 to million times. And these experimental and numerical-based predictions, they somehow disagree with what natural observation, especially mantle tomography, is telling us about slabs sitting in the mantle. Because due to the unprecedented resolution of US array, seismic tomography of Western US shows very highly fragmented slabs sitting at depths of 300, 400, and deeper. And they are kind of looking blobby, strongly deformed. And this cannot be expected from, rigid slab behavior. Dave Stegman and his co-workers, they try to evaluate this, the slab properties numerically. And they were trying to explore different slab to mantle viscosity contrasts to obtain these blobby slab models. And what they found out was very surprising, because the viscosity contrast required for such a slab behavior so that they become highly deformable in the mantle was such low that it was contradicting to any of these experimentally based laws. So it was, no more than 100, and very frequently it was less than 10. So which means that slabs are highly deformable, or at least some of them are highly deformable when sitting in the mantle, while they should be rigid at the surface to preserve the coherency of plates and have this contrast in between rigid non-deforming plates and weak deforming plate boundaries. So as a result of this and other investigations, the paper came around written by Robert Peterson, Dave Stegman, and Paul Tuckley, the subduction dichotomy of strong plates and weak slabs, where they assembled all these different evidences suggesting that there is a magic switch in the strength of the slabs when they go to subduct. So they are strong at the surface, but as soon as they start diving into the mantle, they are becoming much, much weaker. And of course, mechanisms of this weakening, they need to be clarified and understood. So in one possible, approach to understanding of this slab weakening is to focus on the slab bending, because any subduction is associated with the downward bending of the tectonic plates, which is a prerequisite of its diving into the mantle. So we cannot imagine any change from horizontal motion to downward and oblique motion without bending of the slab. And this bending is not fully elastic, it's irreversible in terms of deformation mechanism. So then we can expect a damage and weakening of plates within this bending region. And bending process is universal. All slabs are bent. Some are more than the others, but this is the unavoidable mechanical process that is associated with subduction. So it's very universal and can potentially be a universal explanation to this weakening of mechanical properties of plates going into the mantle. So it's also very well known from multiple observations that this process is associated indeed with the reversible damage reflected by the development of multiple normal faults. Some are small offsets, some are very large offsets to some kilometers that are present at almost every trench with different faults magnitude and extensive or less extensive development, which is also not very well correlated with any of the kinematic or generic subduction parameters. So also on the basis of seismic studies have been suggested. However, this is still debatable, that faults can serve as conduits for water percolation into plate interior, and as a result, deep hydration of slabs can occur near trenches as a part of the process of this slab bending. There are some models, as for example published by Manuele Facenda back in 2009, where he was suggesting that deviatoric stresses can be large enough to cause downward water suction. This is, however, an issue on the debate, because Jude Karinaga was arguing against it and was rather suggesting that it's a cracking of plates rather than water suction, which is causing the seismic velocity anomalies. But what is not denied is this pervasive damage of plates by normal faulting that occurs at trenches, because we see these observables almost everywhere. And then, of course, the structure penetrate deep into the slab interior. So top of the slab can be irreversibly then weakened by this brittle faulting and presumable hydration and cracking. But we do need pervasive weakening of slabs to make them weak and deformable in the mantle. So bottom of the slabs, where most of the strength is hidden at this brittle-ductile transition, should also become weak. And what physical mechanisms can be responsible for this weakening? One possibility, one obvious possibility is this grain size reduction. So based on xenoliths data and based on observations of deformed rock complexes, both from the mantle and from the crust, we know that under condition of intense deformation, there is significant reduction in the grain size which creates such things as mylonites, where originally large grains are destroyed, and instead an aggregate of very fine-grained materials is formed. And of course, the reduction in the grain size also weakens rocks. And as the result, diffusion creep is, for example, strongly grain size sensitive. The smaller is the grain size, the weaker is the material. So one can assume that in principle, this process, if happening in the interior of the slab, can weaken the slab and make them pervasively weak, both on the top where they're weakened by the brittle deformation, and in the bottom and middle plane where they're weakened by this ductile grain size reduction due to bending in the ductile mode. So there is a good theory of grain size reduction for multi-phase material that has been developed by David Birkovici, Yarin Ricard, and co-workers, where they take into account that, in the presence of secondary phases, which are always present in Earth's crust and mantle, such as in the Earth mantle, the dominant mineral is olivine, but there are also secondary phases such as pyroxenes and garnet and spinel and so on. Under such condition, the grain size reduction and regrowth process is asymmetrical in its nature. So it's more easy to make a reduction of the grain size rather than regrowth, because the secondary phases, they will be pinning the growth process and will not allow reduction in the curvature of grains and in the surface energy. As a result, this needs to be taken into account in the models of mantle and crust deformation if we would like to take properly grain size reduction processes which are time dependent, temperature and pressure and stress dependent of multi-phase materials. So, and this is what was the idea of the project that we started with Dave Birkovici. So we have taken one of our standard subduction models. We were using this so-called spontaneous subduction initiation, which is, of course, by itself a debatable mechanism. But what we wanted to have is to avoid, any uncontrolled forcing from the ridge push or plate motion prescribed in the model. We just wanted subduction to start naturally and then see, how the character of subduction will be affected by coupling of the brittle deformation on the top of the slab with normal faulting and ductile deformation with grain size reduction and Zener pinning in the middle and lower plane of the slab. So, all physics which we consider relevant for the slab deformation processes in the outer rise was placed into the model. And the result was quite surprising. Here on this diagram, you see on the top diagram, the development of the grain size. So blue means very low grain size. And then you immediately see that during the subduction initiation, some initial bending of the slab start to happen. And then exactly near the region of the brittle ductile transition, we see this blue cloud, which implies strong reduction of the grain size. And it's not surprising because there we have very high stresses since material is still quite rigid and of high viscosity, and it's subjected to bending stresses. And on the other hand, deformation is also significant. So we need some, 10% of the deformation to accommodate this bending. So here we see the viscosity picture, and not surprising that viscosity is somewhat reduced on the top of the plate where we have brittle deformation, effective viscosity, and in the bottom of the plate where we see this grain size reduction. What starts to happen afterward was quite surprising when we have seen results of these numerical experiments, because what happened is we started to observe non-uniform deformation of subducting slabs. Instead of being subjected to uniform grain size reduction in the lower middle plane of subducting slabs and just gentle uniform bending, what started to happen is this segmentation. Essentially, deformation on the top of the slab focuses in the region of development of normal fault, and underneath these regions, you see the segments of intense grain size reduction, which have triangular shapes, and they are breaking slab into individual segments, with the length of these segments being proportional to the age of the slab. So we started to see this segmentation process, which has never been suggested for subducting slabs And then, of course, very obvious, three-dimensional imagination leads us to this, breaking snake or bending snake on this Kit Kat chocolate. So essentially, slabs, instead of being uniformly and smoothly bent, they're behaving like this Kitty Cat chocolate. They are breaking along the length of the slab within these specific segments, and the length of the segments is defined more or less by the thickness of the subducting plates, which is regulated by the age. So the slab is not weakened equally everywhere. Instead, there are segments boundaries which are very weak, and there are also segments themselves which remain rigid. And then the flexibility of the slab and its easiness in deformation is essentially given by the alternation of these weak and strong slab regions. And again, I'm repeating, so these should be continued along the length of the slab. The model is two-dimensional, very obviously, but it implies that in third dimension we should have some uniformity in the position of these segments along the trench. So at a higher magnification, what we start to see, how this feedback happens. So on the top, we develop strong focusing of normal faulting. Instead of being distributed, it starts to be localized, and we have large offset normal faults, which are also very well visible here. And then beneath this large offset normal faults region, which develops very close to the trench or underneath the forearc at shallow depths, then we see this viscosity reduction triangle, which is characterized by very low grain size under condition of focusing of deformation and very large stresses, which are leading to dislocation creep and associated grain size reduction. So as a result, we have this segment boundary formed, and then the next boundary only form after significant amount of the slab has already subducted. So you need to subduct some critical lengths to start forming the next segment boundary. And the mechanic and the physics of this process is always the same. We have focusing of brittle deformation due to the fault weakening, and then the slave process is this grain size reduction, which is responding to brittle localization, and then produces this nicely formed triangular segments boundaries. So it can continue in the same manner for a very long time. So the process is self-sustained. And when we try to find out what is the master process and what is the slave process, then we performed some experiments where we were activating different weakening mechanisms. For example, this is experiments where fault weakening, strain weakening, and grain size evolution are both present. And then we see the segmentation of the slab is well developed, and there is no doubt that this process happened here. However, if only fault weakening is introduced, this segmentation does not disappear completely, but becomes quite rudimentary. So if there is no feedback from grain size reduction, so here grain size reduction was fully deactivated, then instead of segmentation, we see only shadows of this segmentation. So length of segments does not seem to be very strongly changing, but the segments themselves are not very well evolved, and then also large offset normal faults, they do not develop. Instead, more distributed faulting forms. So still we see that the main reason for this segmentation is coming from the strain weakening of faults at the surface. This is the master process, because if we deactivate strain weakening and leave grain size reduction, segmentation almost completely disappears. So we see this very uniform distribution. Still, there are some undulations, but they are not very well pronounced compared to this picture with fault weakening. So then, of course, if we deactivate both mechanisms, that slabs are subducting as in standard subduction models explored in the past, including myself. So we have nice, very smooth bending of plates, and subduction remains continued for the long time, and so on. So stability of subduction is indeed strongly affected by this potential segmentation process. So then, if stability of subduction is affected by this segmentation, and if we see this segmentation as the natural outcome of the physics plugged into subduction models. We have to convince ourselves that what we are producing in models has any relationship to reality. So can we, and the question is, for which we were trying, to do our best to compare with data is, can we recognize segmentation in the observations? So one of the enigmatic observations that needs to be explained is the presence of these large offset normal faults. Large offset normal fault implies, when they're present at trenches, that instead of distributing evenly the bending-related deformation, we focus them in one place. And what is the reason of such focusing? So the one possible explanation can be that we have this feedback from the grain size reduction exactly in the place where strain weakening of fault is happening, and therefore we have this very strong focusing of brittle deformation and the development of large offset normal faults. And such large offset normal faults are systematically present at trenches, however, not at all trenches. And by the way, there is no good correlation between general subduction and plate parameters and occurrence or non-occurrence of these large offset normal faults. So they can be present at the part of the same trench, and then, for example, in case of Central American trench, and then we move into the other part, and there are no large offset normal faults. However, this can be relatively easily explained if we take into account the segmentation process, because segmentation process is transient, and therefore the chances of finding the slab in the middle or at the culminate stage of the segmentation process, they are quite random. So in many cases, what we see is just the beginning of this segmentation process where large offset normal faults have not yet developed. And since this process is self-sustained, it may not necessarily be related to anything in terms of subduction parameters. So we just find ourselves randomly in the certain position of the segment development in time. So this would explain why we do not have these correlations of the offset of normal faults and subduction parameters. This transience is also by itself is a good explanation to some of the available data on normal faults in terms of their global distribution at different trenches. So second possible observation to be taken into account, it's very well known that grain size reduction produces reduction in the seismic velocities. So then potentially it implies that seismic velocity anomalies inside slabs should be segmented, as well as predicted by numerical models. And I was, when I have seen these blobby slabs in the past, I was always joking when speaking to mental, tomography people that you are doing something wrong, with your mental tomography for the reason that you see this blobby slab behavior, while in models we see this very smooth and very nicely distributed slabs without any internal heterogeneities in their structure. So, but in reality, I was wrong, and these people were right, because indeed, intensity of seismic velocity anomalies inside slabs can be very strongly dependent on the intensity of grain size reductions, and this segmentation within slabs with periodicity of this segmentation, it's quite comparable with the prediction from models with corresponding plate ages. And moreover, with this, like in case of this Kit Kat chocolate, positions of segments boundary inside slabs are not random, and they do not change randomly along the trench. So if it would be inaccuracy of mental tomography, we would see them all the way around, but they are always staying more or less at the same length of the slab counted from the trench. So essentially this Kit Kat chocolate picture is preserved in the mental tomography. And this was very striking. So we only found this data when we were doing revision for our paper. So we did not know anything about this data before we started to do the analysis. And this convinced us that there is some ground truth in this prediction that slabs are segmented in nature as well as in models. Another very critical and interesting observation, of which we did not know when we performed experiments, was the presence of low viscosity anomalies in the slab interiors near the trench and underneath the bending regions. So the prediction for models is that underneath this area where we observe large offset normal faults, as in Japan, for example, there should be also low viscosity anomalies. However, I did not know that such viscosity anomalies can be discovered. And this was the moment of truth when I've seen presentation from Thorsten Becker at ETH Zurich, where he was showing their interpretation of post-seismic velocities after Tohoku earthquakes, which forced them to assume that there is a weak lower middle slab region sitting exactly underneath this outer ice bending region in Japan. Otherwise, the seismic velocity, post-seismic velocity could not be explained in a proper manner. And this is, was the moment when we started to collaborate with Thorsten, because we have seen something that we did not know in advance and that model predicted, and we did not know that such data are potentially available. So, and then it was a very good idea to involve Thorsten, because he also found these segmented seismic velocity anomalies in the Japan slab, which finally convinced us and reviewers that this is the the existing phenomenon of slab segmentation. So as soon as we were convinced that this process has a good relationship with the reality, so which means that slabs are indeed, or at least some of them are indeed segmented when they subducted, we started to think about implication of this process for the stability of modern style subduction and plate tectonics. It was very easy in the past to obtain continuous subduction with the smooth bending. However, this segmentation is disruption of the slab mechanical properties, which may potentially lead to slab fragmentation, breakoff, and other, of course, in quote mark, undesirable consequences. So, and then what we started to do, we started to test models with higher mantle potential temperature, where this physics was not or was included. And then if we do not include this physics and feedback, so if we do this, fault weakening, but no grain size reduction, that subduction becomes faster at higher mantle potential temperature, because mantle impose less resistance to the slab movement because of the lower viscosity. But subduction was continued and stable. So this 150-degree mantle temperature increase did not produce anything, severe for the stability of subduction, except speeding up the subduction quite significantly. However, when we started to explore for the same mantle temperature with coupled rheology models, what we started to observe is that support from the mantle goes too low, and as a result, viscous resistance of the mantle does not allow slab, low viscous resistance from the mantle does not allow slab to preserve coherency. So the weakening of slab segments is such strong that slab subduction from continuous modern style mode, which can last for many tens or even hundreds of millions of years, it becomes intermittent, and then it can easily end up with the slab breakoff and disruption of the continuity of subduction. So essentially modern style of subduction that we observe now with this continued long-lasting subduction is not anymore possible under condition when slab damage is pervasive inside slab. So slab segmentation essentially disrupt continuity of subduction at high mantle potential temperature, and then you do not need extreme increase in the mantle potential temperature. So 100, 150 degree Kelvin above present, increase above present is sufficient to destabilize the modern style of subduction. It does not imply that subduction is not anymore possible. It's possible, but it should be more intermittent, disrupted, so less continued than it happens now. So essentially modern style of subduction and plate tectonics might be quite strongly limited by this slab segmentation mechanism. So it has been repeatedly suggested that, of course, here I'm on shaky ground because it's still the matter of big debate when and how did subduction and plate tectonics started on Earth, but it has been repeatedly suggested that, style of subduction and plate tectonics and tectonics in general was changing through geological times. And, one of these recent assessments suggesting that, the true subduction and plate tectonics only started relatively recently, where, within the last billion year or so, when conditions for, modern style continuous subduction and global plate mosaic was met due to the changes in the mantle temperature and mechanical properties of the slab. And essentially, this is approximately where we would expect the range of the mantle potential temperatures, 100, 150 degrees above present, which are enough, to destabilize the continuous subduction due to the slab segmentation processes. So it seems to fit into this, late onset of plate tectonics, this prediction from the coupled models. So if slab segmentation is real, then we can make the next step and say that perhaps, the modern style subduction was limited by very strong slab segmentation tendencies until very recently. And intermittent subduction was much more dominant than we believe in the past, which was making plate tectonic styles, or in general tectonic styles, dissimilar to modern day Earth in the geological past. So here is, the holistic picture based on models and natural observations, suggesting that, mantle potential temperature was gradually decreasing from Archean time toward present day. And then, in before Archean time, we had probably the squish elite regime, where dominance of vertical deformation, plume lithosphere interactions, delamination, and drips was driving global tectonics. Does not mean that episodic subduction was not possible, but it was not dominant mechanism for the tectonic evolution. Then we move toward the episode of hot plate tectonics, where presence of the depleted mantle underneath moving plates was allowing for building of cratons and continental domains. Then there was this probably episode of quiescence, probably single lead or quiescence episode, after which, corresponding to boring billion, after which, conditions for continuous subduction with some plate segmentation have been created, and this is started the modern episode of plate tectonics. Of course, this picture is highly speculative, but, at least physics put into numerical models would agree to some extent with this overall view. So moreover, further, consequences can be derived from this very late onset of modern style plate tectonics, because then in this case, the modern style plate tectonics arise together with the accelerated development of complex life on Earth. And then one can start connecting, these phenomena also in a speculative manner, but there are more and more evidence from, present day observation and modeling in biology and ecology that plate tectonic processes, they drastically accelerate speciation rates, which may contribute to the rapid development of life diversification and development of complex organisms and their prevalence and dominance, specifically on land, where habitat fragmentation and modification is strongly accelerated by tectonic processes. So the acceleration, according to different researchers, can be of the factor of 10 or 100. So this would explain, why do we have us on this planet in a way. So because at the onset of modern style plate tectonics, evolution of complex organisms was so much accelerated that we had enough time to develop ourselves within this 1 billion year. So if we imagine that evolution would stay, 100 times or 10 times slower, we would be nowhere, because we need another 10 billion years to develop humans on a planet, and we simply do not have this time for the development. Of course, these are highly speculative lines of research, but they are gaining more and more attention from the communities because new computational tools develop which try to connect tectonic and geomorphological processes to life evolution, and predictions from these tools agree also with natural observations and suggest strong acceleration of speciation rates by tectonic processes corresponding to modern style plate tectonics. So if you want to learn more about this line of research. Here is the video recorded by Bob Stern on YouTube, so you can look at it and make your mind whether this is real or still to large extent imagination. Moreover, very interestingly, this type of research and considerations, it may also have quite significant bearings and influences on the exploration of exoplanets, because probably it's very difficult to discover worlds with any life, because primitive life signature can be quite debatable. However, conditions for complex life development, if we suggest that for rapid acceleration of life evolution we need continents, oceans, and plate tectonics, then of course the planetary conditions in this term can be narrowed down quite drastically. So, and we can even tell, this is what I was trying to advocate during the recent EGU conference, that civilizations and intelligent life can only develop on the planets with oceans, continents, and plate tectonics. And such planets, they are quite rare, because to meet all these conditions, only much smaller part of available terrestrial planets can be appropriate for that, and this is much less than 1%. So if you would like to learn more about this hot debate, you can look at this press conference, which is very entertaining. So here I'm done with my presentation of slab segmentation and consequences. And the conclusion that I would like to spell out is that we believe that subducting slabs are segmented by bending due to the coupled brittle-ductile damage in the outer ice region. Slab segmentation allows to explain dichotomy of strong plate and weak slabs due to this, plastic snake mechanism of bending, or KitKat, geometry and deformation way of the slabs. Then large offset normal faults and their random appearance at different trenches can also be explained by the transience of slab segmentation process. Segmented slab seismic velocity anomalies may correlate well with the slab segmentation at outer ice, and then low viscosity region observed past the Tohoku earthquake in the close to the Japan trench may also be the consequences of this slab segmentation process. And last but not least, slab segmentation might be a critical phenomenon in limiting stability of continued long-lasting subduction, which creates and defines modern style plate tectonics, and perhaps transition to this modern style plate tectonics happened as late as in Neoproterozoic, and also accelerated life evolution to create us on this planet. Thank you very much for your attention.
All right, thank you, Taras. Can you hear me?
Yes, absolutely.
Great. Okay, we're going to switch to question and discussion. Just let me know, Taras, if you need to go, because we don't usually cut this off.
Oh, no, not at all. I'm freed for the rest of the evening.
All right, then in that case, what we will do is allow people to ask questions either by raising your hand. You can find that in the reactions at the bottom. So click the reaction button at the bottom of your screen and click raise hand, or you can type it into the chat, please, to everybody. So
that I see Kent would like to ask a question.
Great, go ahead, Kent, please.
Very interesting results, Gerya. I was wondering, there are many slabs today that don't show segmentation, aren't there? I mean, I look at a lot of seismic tomographic profiles of slabs and don't see evidence for this segmentation. So what's going on that some slabs show it and some slabs don't show it?
Exactly. Thank you very much, Kent, for this question. Yes, correct. Of course, there is a big question of the quality of data for mantle tomography, because we shown Japan as an example where we have this unprecedented high resolution, which is capable of resolving these slab segmentation process. However, we have also seen that at certain intensity of bending process, reduced intensity for flatter slabs, we do not always necessarily see this segmentation. So slab segmentation may not necessarily be unavoidable. It has been identified as a new phenomenon, but I should say we do not have systematic study that would, suggest on how many slabs in nature can we expect this segmentation. Perhaps, modeling of specific subduction systems would be the way to try to do it. And also, of course, we do need very high resolution of mantle seismic tomography to be able to resolve these slab boundaries, because the resolution issue can always come. The only, the good thing about this segmentation is that we can predict geometry to some extent. So it's not any segmentation of anomalies. It should remain continued along the trench, because if it starts, essentially, you are creating this, narrow, long plate segments, which needs to be present and discovered. So if we simply see heterogeneity, it does not imply segmentation. So what I can say is that there are good hints that this mechanism of slab deformation is real. However, it's correct to say that we do not have, sufficient representative natural data to tell where and how much of this slab segmentation occur in nature. I see this as an interesting future research directions.
As a follow-up on that, is there any relationship between the dip of the subduction zone and whether segmentation occurs or not?
It seems that the more steep subduction, the more bending one obtains at the outer rise, the bigger are chances to create this slab segmentation. So essentially, very flat slabs with moderate amount of bending at outer rise regions, they may not necessarily be subjected to any segmentation. However, this process is three-dimensional, and there are yet no three-dimensional models of slab segmentation, which needs to be also kind of explored in the future. So simple hint would be less bent slabs should be less subjected to segmentation. So then shallowest deep-in slab should be probably less segmented than steeper deep-in slabs. But this is more speculation than the result of systematic investigation.
Thank you.
I see Michael Brown.
Yeah. Mike Brown, go ahead, please unmute yourself.
Hi, Mike. Good to see you.
Good evening, Taras. How are you doing?
Fine. Recovering after COVID, believe or not.
Can you go back to the slide with the mantle TP of plus 150?
Yes. Yeah, exactly. This one.
What determines that the slab breakoff occurs at that particular weak zone rather than the previous one?
Yeah, I think mostly determines, how much of slab pool is present, because the strength of the segment boundary is limited, say, 200 MPa or so. We did not evaluate, but this is my, intuitive feeling. And then you need to create certain chunk of the slab which will pull and create this stress at the segment boundary. So then the slab was too short for previous segments. And then as soon as you subduct it to 100 kilometers, it start breaking off.
Right. So the length determines the stress. And once the stress is greater than the strength of the weak zone, it breaks off.
Exactly. Yes. Yeah. And the condition of colder mantle temperature, support from the surrounding more viscous mantle, it prevents from creating this high stress at the segment boundary and significant deformation.
Right.
Okay, so I'm going to go ahead and ask one from the chat here. Is there a minimum threshold? This is from Kaysendur Sarwan. Is there a minimum threshold for grain size reduction? And if such a threshold exists, what factors would affect this threshold value, like mineralogical composition or temperature of the mantle, etc.?
Yeah, thank you very much for this question. Indeed, it looks like, for creation of pervasive slab segmentation, grain size should reduce to, some tens of of micron size. Whether this is feasible or not, it's also dependent, of course, on the model of damage, which is to large extent experimentally calibrated, but there are still some free parameters. So I would say it's not within the unrealistic range. Such grain sizes of some tens of microns are observed, in natural mantle xenoliths under condition of mantle deformation. But frankly saying, this issue needs to be better investigated, because there are these petit spot volcanoes, for example, near the outer rises, which may potentially bring mantle xenoliths. They needs to be investigated if this degree of grain size reduction is achieved underneath the outer rises or not. So this is more or less how I can answer the question. Thank you very much.
Okay, next one up is from Don Davis. It says, mantle viscosity depends on temperature and mantle hydration, but the only way to get water into the mantle is by subduction. So doesn't it follow that viscosity may have been high even at high temperature, preserving segmentation?
Yes, exactly. Yeah, it's not only water, but it's also grain size regrowth and mantle depletion, which would suppress somehow this Zener-Pinin mechanism. So there is a potential of extending stability of subduction, back in geological, continued subduction back in geological past, and there was an episode of this old plate tectonics, which may imply that under condition of stronger mantle depletion, for example, and less water available at deep depths, so mantle was still strong enough to support continued subduction. Probably not for half a billion or billion year time, but at least for some period of time. So there might be also a sweet point in the slab property in terms of segmentation. Probably the biggest segmentation needs some intermediate degree of mantle depletion, which can only be achieved at intermediate mantle potential temperatures. So probably this boring billion was a sweet spot when this continued subduction was fully deactivated, while further back in time, due to the mantle depletion, continued subduction was more likely and perhaps appearing. So there are certain further consideration, I agree, that may not necessarily imply simple picture, so that we have intermittent subduction all the way through the history, and then continued subduction started in the last billion years. Thank you.
Okay, Jean Bedard, go ahead, please unmute yourself.
Hi, Taras. Really interesting.
Hi, Jean.
Made me think. What does this do to the slab pull force? If it's segmented that way, there ain't none, right?
Yeah, exactly. So potentially slab pull force, of course, depends on the age of the slab and the rate of subduction and so on. So I think it's very well known that most of the energy dissipation during subduction is happening in the mantles. Essentially, most of the resistance to this segmentation process may come from the mantle rather than from the slab itself. So therefore, in a way, mantle can serve as a carapace for segmented slab and preserve its coherency and continuity, even if, in fact, strength of the slab is not very high, simply because deformation of the surrounding mantle will not allow the stretching of the slab and break off. So then I think
like when you're siphoning water through a hose, the liquid has no strength, but just another observation. You might have heard about pit spot volcanism that occurs where the slab bends. That would also weaken it even more.
Yes, and what is interesting about this petit spot volcanism, that it happens also, very close to the outer rise, and it's interesting from several points of view, because first of all, is it also enabled by this, this slab segmentation process? One possible question. And second, does these petit spot volcanoes bring us any information about presence or absence of this grain size reduction in actual materials with the lower grain size? Because we can easily predict that there is significant amount of deformation under high stress condition during the slab bending, but we do not have physical evidence of this grain size reduction except this viscosity reduction regions reflected by post-seismic velocity anomaly. So having, you know, real world data would be very attractive, but I'm not sure how feasible it is to get anything like xenoliths from these petit spot volcanoes, because they likely do not expose to the surface, right?
I was thinking more in terms of if you have a fault parallel to the subduction zone and you inject that with magma, well, your strength just gone to zero. So that would accentuate the process you're talking about.
Yes, I agree. And however, even without presence of these PT spot volcanoes, it has been suggested that, you know, the friction coefficient reduction along the outer ice normal faults can be, you know, predicted on the basis of fault orientations. And essentially, you know, what we put into the model is from, you know, friction coefficient 0.6, it goes to friction coefficient 0.3, and this is good enough, you know, to strongly promote the slab segmentation tendency. And this is what was, you know, suggested on the basis of observations for, you know, normal faults, earthquakes close to the outer ice. So, you know, the effective friction coefficients on the order of 0.3, 0.2. But of course, further reduction can be expected from any magma percolation through these faulting structures.
All right, Daryl Long, you're up next. Please unmute yourself.
I see Daryl.
Daryl, you're not quite unmuted. I'll send you. Let's try that
again. I'm unmuted now.
There you go. We get. I might have screwed it up again, Daryl. Sorry.
I've done it twice. Okay.
There you go.
With these, essentially the downgoing slab moving in segments, is there any recordable signature in the forearc basin that you could tie to this?
Yes, absolutely. Yeah. So I was hoping that, you know, we can find some episodic record in the forearc in terms of probably fission tracks or anything that would be possible to, you know, compare with the topography evolution caused by the slab segmentation, because topography evolution on the time scales of several millions of years seems to be quite pervasive. And I even done, you know, topography interpretation on this uplift and subsidence rates in the forearc. But since I was not able to find any, you know, straightforward data to be compared with models, I left this, you know, line of research for future to some other people who may hopefully become interested. But you're absolutely right. Slab segmentation has direct consequences for the forearc topography evolution. And there should be alternation of uplift and subsidence episode major on the scale of the entire forearc on the time scale of few millions of years, which is the episodicity of the segmentation process.
Okay, that's great. Thanks.
Okay, next up, Felix Gervais. Please unmute yourself.
Yes, thanks, Taras, for a great talk. It's intuitive to me that, you know, the segmentation will lead to more breakoff, but your previous study with Sisova that is shown on the top right corner of that slide that is shown right now already convinced me that just increasing the mantle temperature would lead to more slab breakoff. So could you comment a bit about the differences between the two models?
Exactly. Yes. Thank you very much for this question. It's essentially the first person who suggested, you know, the prevalence of slab breakoff at hot and mantle potential temperature was Jeroen van Huden and Arie van den Berg. They published seminal paper in 2008 in Litas, where they have shown that, you know, this tendency arises in modern style subduction models with the mantle temperature increase. The only difference with this study is that typically this break-off tendency become prevalent at much hotter mantle temperature increase. So we need to increase mantle temperature by 200, 250 or 300 degree, essentially somewhere corresponding to Archean time, to have this intermittent, highly intermittent subduction. Before that time, subduction behaves in a very continued manner. So if we just increase by 100 or 150 degree, nothing happens. Essentially here, to obtain slab breakoff, we need further 100 degree or 150 degree of mantle temperature increase. And slab segmentation process, essentially, it makes slab even weaker. And then this breakoff and intermittent subduction tendency apparently appears much early back in time that was previously anticipated. So in principle, the novelty is not in that phenomena has been suggested, but it just, that this phenomena has been moved, more in time toward the present day as a result of this study.
So okay, thank you. So apart from weakening the plate with deformation, there's no much change in the parameters between the models?
Exactly, yes,
okay.
Yeah. However, character of, of slab deformation changes quite drastically. So as you can see, this is, classical subduction models with smoothly bent slabs, which I was exploring myself, for a very long time. And then this is the segmented slab deformation, which was discovered in numerical models. And then we were not sure how, real is this phenomenon. Now we are more sure, but still it needs to be evaluated by comparing models to more systematic data around the world.
All right, thank you.
Thank you.
Okay, Lyle Harris had something he may want to show or discuss. So Lyle, would you like to chime in?
Well, I'm just wondering, I think I've got an example of just what Taras has been showing. I don't know if it's possible now to show an image. If not, I'll just send it to Taras later on.
It should be possible if I can, unshare my screen.
Yeah, if you unshare your screen, we should be able to get Lyle's shared.
Yeah, exactly. Thank you.
All right.
Okay, so that's just an example I had from a presentation of some work looking at in Greece. So this is just a figure from a publication here of subduction underneath the west of Greece, where there's been the drip and delamination for the Château core complex. But at the same time, I looked at the seismic tomography, so a detailed study there, and I'd been surprised that, we can image the slab really well, but there are all these blobs that have accumulated through here, and then we see beautiful breakoff, and then just the base of the slab sitting here at the 660-kilometer discontinuity. So I'm thinking that, I wondered, why are we getting all these blobs accumulating? But that really could be just what, Taras, you were showing. So I don't know what you think about that, whether that could be an example.
Yeah, this could be real in my opinion, but the consequences of slab segmentation is that these planar long segments are created. Of course, they can also be deformed along the segments. But since I did run some 3D models, but I did not do any systematic studies in which three-dimensional deformation of the slab has been investigated under conditions of slab heterogeneity. So it may be real, or it's probably likely real, these mantle tomography pictures. But whether slab segmentation is a good explanation for all complexities, this I don't know. I think, one needs really to perform three-dimensional modeling in a systematic manner to, find out which geometry should be characteristic for relatively complex short slabs subjected to complex deformation.
Okay, I'll send you the 3D PDF of that, so you can play with that. Okay.
Yes.
Okay, let's see. Everything kind of reorganized on me here. We have another one in the chat from Case Under again. Is it plausible to calculate the Reynolds number for the surrounding mantle and the fold and color coding it and plot it in the model? And a follow-up question, would this be useful to understanding the dynamics of the mantle flow surrounding the subduction zone, i.e., how would the subduction be altered if the flow is more turbulent or more laminar?
Yeah, frankly, I cannot properly answer this question because what we are using in the model is quite complex nonlinear rheology, and then they're not so easy to interpret in terms of the Reynolds number. In addition, I think this investigation of the flows around slabs and the effects from slab segmentation on these flows would be best to investigate with global models and three-dimensional models, because typically what has been shown in the past, the flow around slabs is already very complex, even if continued and gently bent slab are considered. But if they will become segmented in different directions, then there will be, I'm sure, quite strong complications from the flow pattern. But in general, this is very interesting and important idea, because I think, in the end, it's also global mantle convection modelers who should, try to implement these physics into their global mantle convection and plate tectonics models, and find out if including of these physics will have, any effects on the stability and transition to modern style plate tectonics or not. Because so far, this physics has not been fully explored in the global mantle convection models. Probably also resolution is an issue.
All right. In Adrian Tasistro Hart, sorry if I mispronounced. Please go ahead and unmute yourself for your question.
Sure. Hey, Taras, it's Adrian here.
Hi.
So I think, a notable feature of the Phanerozoic is extensive shallow marine flooding of continents, well into the continental interior. For example, the slough sequences of North America, and these are often attributed to dynamic subsidence resulting from subduction underneath the continent. And so I'm wondering if you have any thoughts about that being maybe a relatively novel phenomenon resulting from the onset of modern subduction like you're describing here.
Yes,
and if that might play into the story of evolution that you're presenting.
Thank you very much for this question. Indeed, the development of large coherent slab segments underneath continents may control, lots of these phenomena that have been observed at the surface, because intermittent subduction with frequent slab fragments falling on 660 discontinuity will not create the same mantle dynamics and the same mantle buoyancy distribution as this very long-lasting continuous subduction. So I think there are further consequences from the establishment of and stability of the continuous subduction and global plate mosaic on the evolution of continents in terms of their topography and interior and so on, which needs to be understood. I think this is very fruitful direction to explore this change in the style of subduction, whether or not these, many of the natural observations that we have for the, last billion years can be explained within this paradigm of changing subduction and tectonic style to the modern one.
Okay. With that, I don't have any more questions in either the chat or hands up. So big thanks, Taras. That was great and generated a ton of discussion. Really, really cool to see your models, for sure.
It was very cool to see you all and, to have this very nice discussion. Thank you very much all for participating. It was a pleasure to see you guys.
Yeah, bye-bye. Thanks, Taras. All right, everybody, take care.
Take care.